Okay, so now we're going to move into the Electron Cloud and talk about how electrons are actually occupying this space. So first, electron shells. It's very simplistic, but a useful way to look at energy levels or shells is to use the periodic table, so that the energy level is represented by the row number. So row 1 is the first energy level, row 2 is the second energy level, row 3 is the third energy level, so on and so forth. Electrons go into the shells or energy levels. The energy levels are called the principal energy levels. You could say 1 to 4, but you could go above 4. Theoretically, it could go forever. The maximum number of electrons that each energy level can hold is 2n squared. It might be useful to remember that little formula where n represents any of the energy levels. And so if we're on the 4th energy level, we would say 4 squared is 16 times 2 is 32. So there's 32 electrons that can go on the 4th energy level. Make sure you remember the order of operations and that you square before you multiply by 2. The energy levels can be subdivided into sublevels. So you have energy levels that break into sublevels, and the sublevels are our SPDF. The first energy level has one sublevel, which is S. The second energy level has two sublevels, S and P. The third energy level has 3, S, P, and D. The fourth energy level has 4, S, P, D, and F. So the number of the energy level that you're on is equal to the number of sublevels within that energy level. Now, to go beyond F, you would just continue with the alphabet, skipping over S and P when you get there. Each type of sublevel can hold a different number of maximum electrons based on the number of orbitals. So S has one orbital, so it can hold 2 electrons. Remember, we would show that S with one line. And then P has 3 orbitals, so we would say P, and then we would draw 3 lines. 2 for each would make a total of 6 that could go into the P. D has 5, so we would draw D, and then 5 lines, so that's a total of 10 electrons. F has 7, so that would be a total of 14 electrons. So you have energy levels broken into sublevels, which could be broken down into orbitals. Aufbau's principle tells us that we want to fill from the lowest energy to higher energy. We use the diagonal rule in Chem 1, so I believe this is the way I drew it on the board for you, except we had one S on the bottom, and then we would work our way up. You could also look at it like this, where you're going to fill 1S, and then 2S, and 2P, and 3S, and 3P. Then it fills the 4S, so that's where the blip happens. Then you fill 3D, 4P, so on and so forth. Just make sure you know the order. You can remember it by either of these pictures, or you can use the periodic table. So if we look at the periodic table, it still fits. You have 1S. Make sure you're reading from top to bottom, left to right. So 1S, 2S, so groups 1 and 2 make the S block. And then second row, that's the first time we have the P block. So groups 13 through 18 would be the P block. 3S, 3P, 4S, and then here we have our D block, which is groups 3 through 12. And then it goes back to the row number for D. So remember, the D block is 1 less than the row that it's in. We don't come across the F block until we reach this point. So after 6S, you would come down here to 4F, then you would go back to 5D, 6P, 7S, come down to 5F, and then back up to 6D, and 7p. So it can get a little complicated down here where you have to jump down to the F block. But remember, the atomic numbers are in order, so you should see a jump between these two elements, indicating that you need to come down here. And we do 6s, and then we do 4f and come back to 5d. So how do you write electron configuration? The large number is your energy level, then you have your sublevel, and then the number of electrons in that orbital. The order in which the energy levels are filled is again called the Aufbau principle. So if we look at magnesium, magnesium on the periodic table is number 12, so it has 12 protons. It's found right here. So we would say 1s2, 2s2, keep coming across, second row still, 2p6, 3s2. So there's the electron configuration. Sulfur, which is number 16, is found right here. So again, starting at the beginning, 1s2, 2s2, keep coming across, 2p6, 3s2, again, puts us at magnesium. We're going to keep going. 3p, and then sulfur is the fourth element in, so it's 3p4. Copper, which is number 29 on the periodic table, is right here. So we would say 1s2, 2s2, 2p6, 3s2, 3p6. Sorry. That puts us right here at argon, and then we would say 4s2. Remember, the D block is one less than the row, so this is 3D, and we would count our way across, and we would have 3D9. Now, that's the way we did it last year, and that's fine. That's the way you do it, except there are two exceptions. The two exceptions are when you're half filled or close to being filled D. So there's two exceptions to the Aufbau principle: the electronic configuration of chromium family and copper family. So the chromium family would be group 6 or 6b. The copper family would be group 11 or 1b. They do not follow the pattern, so there's some abnormalities happening, some exceptions. Half-filled 4s is better when you can have a half-filled or filled D. So if we think about the copper that we just filled out, this is not correct. It's better to have the D filled and the S half-filled. So when we write copper, what copper really is 1s2, 2s2, 2p6, 3s2, 3p6, and then instead of 4s2, 3d10, we're going to fill the 3d by taking 1 from the 4s. So one of the electrons in the 4s is going to go ahead and fill out the 3d because that's just more stable. The electrons are happier in this situation than it is with a 4s2 3d9 combination. So for anybody in the copper, it's going copper family, copper, silver, gold, it's going to end in S1 and D10 instead of S2 D9. Now for chromium, if we were to write the electron configuration for chromium, we would say 1s2, 2s2, 2p6, 3s2, 3p6, and then we would have 4s2 and 3d4. Well, since the D sublevel can hold 10 electrons, it's better to be half filled with 5 and take one of them from the S. So everybody in group 6 or 6b ends in S1D5. It's more stable to have this half filled or filled D sublevel than that filled S sublevel. When you're writing electron configurations for ions, remember atoms lose or gain electrons. That's what an ion is. Positive, they lose those electrons, so you're just taking off the last electrons. And negative, they gain electrons, so you're just adding 2 at the end. So for example, sodium would, let's do the noble gas configuration here, be neon 4s1. The sodium plus is going to lose that 4s1, and so its electron configuration would be 1s2, 2s2, 2p6. Sorry, that should be a 3s1. So it loses that outer electron. For oxygen, it would be 1s2, 2s2, 2p4. Oxygen minus 2 is saying, hey, I've gained 2 electrons, so its electron configuration would be 2p6. Now, if you're talking about transition metals, again, it's a little funny. Transition metals always lose their 4s electrons first. So if we think about titanium, which is number 22 on the periodic table, let's write the noble gas configuration. It would be argon 4s2 3d2. So when we say that there is a +2 charge, what 2 electrons is it losing? Well, it's not losing the 3d, it's in fact losing the 4s. So for titanium +2, the configuration would be argon 3d2. Again, transition metals will lose 4s or lose their s electrons before they lose their d electrons. So if we look at chromium, remember chromium would be argon, and then chromium is our exception, so it would be 4s1, 3d5. So to say that we have a chromium 3 ion, what we would do is we would lose the 4s, and then we would lose 2 from the 3d. So chromium +3 would be argon 3d2. Sorry, 3d3. So transition metals lose their s orbital electrons first. Everybody else, it's going to be the outermost electron. And then some just abbreviations, which I've kind of already used. Noble gas configurations, you start with the noble gas that comes before it, and then just continue electron configuration for after. So titanium, we could have written as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. All of this is the same thing as argon. So we can shorten this abbreviation and just say argon 4s2, 3d2 instead. That's perfectly fine. In fact, for DP, it doesn't matter what configuration that you use. They tend to use noble gas because we're really only worried about those outer electrons. Again, orbitals are the energy levels that are made up. They can hold 2 electrons. Sublevels, we've already talked about their different number of electrons. And then the shapes, I have seen questions where they ask you to draw the shape. So remember, S is a sphere. P would be shaped like a peanut. So you would draw it kind of like that, saying that there's no electrons right there at the middle. The sphere you would draw like a sphere. D would be a double peanut. So you would just draw 2 of those like that, or the best you can. And then there's 5 different variations. You don't have to be able to draw the 5 different variations, you just need to know that there's 5. F would be like a flower. And I've never seen a question to ask you to draw F because F can get very complicated to draw. But there are 7 different variations for the F. Orbital diagrams, I have seen questions that ask you. You don't have to do orbital notation unless you're asked. Just remember that the electrons have to have opposite spins when they're in the same orbital, and that when you have more than one orbital, for example, the P and the D and the F, you want to put 1 electron in each before you go back and pair up and that's Hund's rule. So for orbital diagrams, arrows represent the electrons, the direction represents the spin. In one orbital, they have to have opposite spins. That's the Pauli exclusion principle. All right, so use boxes to represent orbitals and give the full electron configuration for the following. Lithium, 1s, and then you would draw your 2 electrons, 2s, 1. For fluorine, we could continue this. And for fluorine, we can add on 2p, 1, 2, 3, 1 in each before you go back and pair up, and there's fluorine. Potassium, again, we could just continue this. Add there 3s2, 3p, 1 at a time before you pair up, and then 4s1. For nitrogen, if we wanted to start again, 1s2, 2s2, 2p, 1, 2, 3. Nitrogen has 3 electrons. They would all go in different orbitals, all the same direction. And so if we were to add on for oxygen, which has 1 more electron, it could go in any of these orbitals, so it doesn't matter as long as you pair that last 8th electron. So remember, electrons enter the lowest energy levels first. That's alpha. They prefer to occupy orbitals on their own, spinning in the same direction, but when you pair them up, they have to be opposite directions. That's Hund's rule and Pauli exclusion principle. Ions, the electrons in the highest energy level, are lost first, except for transition metals, which lose the 4s before the 3d.